Okay, so today I am going to uh, we're going to do we're going to solve the problem kth smallest element in a binary search tree. Uh, so it's a pretty interesting problem, and it uh, which kind of uses the property of a binary search tree to build an efficient solution. So let's talk about what uh, I'm going to assume that uh, whoever is watching this video knows what a binary search tree is. Uh, but we can again quickly give a recap of what binary search tree is. So binary search tree um, is a tree which each node can have maximum two children, and they exhibit a property that the left child of the node is smaller and the right child is larger than the parent. So if you look at this tree, 3 is one node, and three's left child is smaller than 3, and three's right child is larger than 3. And same applies to this node, node 1, which is it doesn't have a left child, which is okay. It can have 0 or 2 at the most nodes or children. But the right child of 1 is 2, which is larger than 1. So, in short, all elements in the left subtree of 3 are smaller than 3, and all elements in the right subtree of 3 are larger than 3. So, that's the property of a binary search tree. Now, what we are asked is find the kth smallest element. So, if you there's one way, not a very efficient way, but there is one easiest way. If you don't get anything, you can code this solution, is to do a in order traversal of this tree and return the kth element from the beginning, right? So an in order traversal of a tree is basically going to of a binary search tree is going to sort the elements from in the ascending order, right? Um, so in this case, for the first solution, it will the in order traversal should return a list which will be 1, 2, 3, 4. And since k is 1, you return the first element. Uh, but again, the time complexity of this is going to be O of n, because you scan all elements and in the tree, and then you also the space complexity is O of n, which is not bad. I mean, for if you don't know how to solve this problem efficiently, then maybe just go with that solution. So let's look at this other one. So in this case, if you look at this as a sorted list, k is 3, so the answer is 3. So in an in order traversal, the way it works is you basically go at any given node, you go to the left subtree first. Once you are done with the left subtree, you look at the current node from where you have gone or from where you are, uh, and then go to the right subtree, right? Um, so can we use this property, and can we make this problem go faster than O of n? And I think the answer is yes. So we just need to track how many nodes we have so far visited. And if that number matches k, then basically take the value of the node at that level and then return that, and then skip everything else because we've already found the solution. So the worst case, if k is like the number of nodes in the tree, then you obviously have to go, it will visit all nodes. But if k is smaller, right, like for example in this case, um, it will only visit these 3 nodes and then skip. uh, so we basically we prune the search space once we have visited k number of uh, nodes in the tree. um, Is that okay? So why don't let's start to code this. So in order for us to um, keep track of the nodes that have been visited, and also to capture the value once we have the kth smallest element, we will basically keep a 2D array called as tracker and initialize it to the first value is number of nodes visited, and the second value is the actual kth smallest element when it is found. Okay, we are going to assume in this problem that k is always going to be less than n. It's actually a constraint. So that's good. So basically what we want to do is we want to return the answer as tracker of 1, which is the once we find it. So basically run the in order traversal k and then pass in the tracker. So let's define this in order traversal. We don't need to return anything from here because we are passing the tracker object, and I'll tell you why we are passing in like this, because in Java everything is passed by value. So in this case we are passing an object, so we can update the state and it's not going to, so we can track our answer. Okay, so there we go. So now if root is null, then don't do anything, just return. Then let's go to the left subtree first, right? So in order traversal k tracker. Now, when we have returned from the left subtree, we want to see if we have, so we know the 0th element in the tracker is the number of nodes we have visited, and we'll increment that in just a second. Actually, let's increment that here. So now we are visiting the current node. So if tracker of 0 is equal to k, so now we basically have visited k number of elements or k number of nodes. So now as we know that we are at the kth smallest element, so basically capture this value of the current node, let's say its value, and then return. Okay, so we don't need to do anything. If it is not, then we basically have to go into the right subtree, right? Okay. And since we want to prune the tree, once we know that we have visited k number of nodes, then we check that and we do if tracker is greater than equal to k, just return. Okay. So let's track this problem with an example. So we start at 5, right? So tracker at this stage is 0. So 0 is not greater than k. So we are asked, so value of k is 3. Okay. And we are currently at 5. So we go to the left subtree, because that's what we want to. We are doing an in order traversal because we want to find the smallest element. If we were trying to find a kth largest element, we first go to the right subtree. It's basically reverse in order traversal, but so we go to the right subtree because um, if you the right trees have larger uh, uh, the values in the right subtree are larger than the root, so we go to the right, then the root, and then left. Okay, so, but we are doing kth smallest, so we go to the left subtree. So we are at 3 now. um, we still pass this condition, we go further left, still pass this condition, we go to 1. At 1 we still pass this condition and we go to the left. So left of 1 is a null, so it returns. Then we come in here, we have marked 1 as visited by incrementing the counter. Is 1 great equal to 3? No. So we go into the right subtree, and this thing goes into the right subtree of 1, which is null, so returns the value. It returns the function call, and we return back to 2. Now we are at 2. 2's left subtree call returns. So now 2, we are going to increment the tracker. So now 2 is marked as visited. Is 2, we're going to check if 2 is equal to 3. No. We're going to go into the right subtree of 2, which is, now we are in the right subtree of 2 with root is null because there is nothing on the right subtree, so it returns. We are back. Now 2 returns back the recursive call for 3's left subtree returns, and we are at 3. So increment 3 tracker again. Now 3 is marked as visited. Is tracker of 0 equal to k, which is 3 equal to 3? Yes. So now we copy value of 3 into tracker of 1, which is what we want, and then we return. Now we are at 5's left subtree call returns, which is where we are. We go into here. So now tracker of 0 is 4. Is 4 equal to 3? No. We go into 5's right subtree. Oh, actually, sorry. That's my bad. We actually go into, when we return at 3, we go into 3's right subtree, which is 4. And we return from here fast exit because now tracker is 3 and number of nodes visited is 3. And when we have already basically found our element, so we return from here. And same thing applies at 5's right subtree traversal. So let's run this and see if it returns. And eventually all the recursive calls return, and we have our answer in tracker of 1, which we calculated here. Great. Yeah, so basically the reason I'm passing the tracker is in Java, like I said, there is, if I just pass this as an integer, it's not going to work because it's passing it by value. So we want the mutated state to be tracked across different function calls, and that's why we were passing it as a reference here. And int of an array is a object, so it will be passed by reference, and we track it here. The key point in this problem is once we have visited k number of nodes, we know that we have found our answer. We copy our answer into the tracker and we return. And then at every iteration, we check if we have visited k number of hosts, visited greater than or equal to, and if we have, we don't need to do anything, we just return. So this way we don't actually visit or do any work when we go to 4 and 6. um, and this 4 and 6 are just not, imagine like this could have like a huge tree underneath it. So we are basically not going to parse that tree, so we save a huge amount of work by uh, using this trick and tracking how many elements we have gone so far, have visited so far. And there is a variation of this problem where it is kth largest element in the BST, and it's just the reversal of this problem. So we'll basically go to the right subtree first, then the root, and then the left subtree. And essentially, it's exactly the same code, except you switch the order of which trees you visit. So that's like a reverse in order traversal. Yeah. So there you go.